All right, if you're gearing up for your Class 12 exams, you probably know the feeling. Organic chemistry can seem like this endless, impossible list of reactions you have to memorize. But what if there's a secret, a pattern that connects everything? Well, stick around because we are about to crack open the playbook that will completely change how you see this subject.
I mean, seriously, have you ever felt like you're just drowning in reactions from chapters like haloalkanes, alcohols, and amines? If you have, you are definitely not alone. It feels like a mountain of pure memorization. But what if we've been looking at it all wrong?
What if all these chapters, which seem so separate, are actually just parts of one big, interconnected story? That's what we're going to dig into. We're on a mission to find that one simple idea that works like a master key, the one that unlocks all of these chapters at once.
Okay, let's dive right in. The one single idea that changes everything is this concept of a hydrocarbon derivative. Seriously, if you can just get your head around this, the rest of the syllabus is going to start clicking into place.
And it really is this simple. A hydrocarbon, right, is just a basic compound made of carbon and hydrogen. A derivative is what you get when you take that simple hydrocarbon and you swap out one of its hydrogens for something a little more interesting, a new functional group.
So this right here, this is the three-step playbook for pretty much all of organic chemistry. Step 1, you start with a basic hydrocarbon. Step 2, you pluck off a hydrogen. Step 3, you stick a new functional group in its place. And that new piece you add, well, that's what defines the entire chapter you're studying. Whether it's an alcohol, an amine, or a haloalkane, it's all just a variation of this one simple move.
Okay, so if we're swapping in all these different groups, who are the main players on the field? Let's meet the families that these functional groups create, and you're going to see all your chapter names start to pop up right here.
This table, you guys, this is your roadmap. Just look at the pattern. You start with a simple hydrocarbon chain, an aliphatic compound, and swap a hydrogen for a halogen. Boom, you've got a haloalkane, your first chapter. Swap it for an OH group instead, and you get an alcohol. Do that same exact swap, but on a ring structure, an aromatic compound, and now it's a phenol. See, even amines fit the pattern. They just start with ammonia instead. It's not some random list. It's a totally logical system of upgrades. All right, let's keep building on this. Now that we know the families, let's look at a couple of their signature moves, the famous reactions used to make them. And trust me, these are the ones that always show up on exams.
So, starting with haloalkanes, their entire identity is built around having a halogen. So it kind of makes sense that their key prep methods aren't always about making one from scratch, but just swapping one halogen for another one that's more useful.
And this is a perfect example. The Finkelstein and Schwarz reactions are basically two sides of the same coin. They're both famous for this halogen exchange idea. In both cases, you start with an alkyl halide you already have. Need to attach an iodine? You use the Finkelstein reaction. Need a fluorine instead? You use the Schwarz reaction. It's the exact same strategy, just different tools for different jobs.
Okay, now for ethers. There is one preparation method you absolutely 100% need to know, not just because it's important, but because it's the perfect example of how two different chapters are connected. And here it is, our first huge connection. Just look at the reactants for the Williamson synthesis. It needs an alkyl halide, the star player from our haloalkanes chapter, to create an ether. See? This isn't just some random reaction, it's a bridge. It proves that what you learn in one chapter is literally the building block for the next. They're not separate topics, they are sequential steps.
So we've seen how to make them. Now let's see what they actually do. Every single one of these families has a few key reactions that define its chemical personality.
For haloalkanes and haloarenes, a huge part of their personality is their ability to couple, which is just a fancy way of saying they join carbon chains together. They're fantastic at building bigger molecules from smaller pieces.
This table just lays it all out so cleanly. The Wurtz reaction joins two straight chains. The Fittig reaction joins two aromatic rings. And the Wurtz-Fittig, well, that joins one of each. Are you seeing the pattern again? It's the same reagent, sodium, but just by changing the reactants, you get completely different structures. So cool.
Okay, this is it, the final piece of the puzzle. We've seen some hints of how these things are connected, but let's make it absolutely crystal clear. The real secret to organic chemistry is that the chapters aren't just related, they are constantly talking to each other.
This slide right here reveals the ultimate secret for mastering conversions. It's a two-way street.
With a simple substitution reaction, you can turn a haloalkane into an alcohol. But, and this is the amazing part, you can turn right around and reverse the process. That same alcohol can be turned back into a haloalkane. Once you get that these reactions are cycles, you don't have to memorize some crazy path from A to Z. You just need to know the simple steps between neighbors.
And this is the big aha moment. That reaction that turns a haloalkane into an alcohol, that's not just one fact. It's two facts for the price of one. From the haloalkane's point of view, it's a chemical property. But from the alcohol's point of view, it's a method of preparation. It's the exact same reaction, just seen from two different chapters. You don't need to memorize twice the amount of information.
So if you take just one thing away from all this, please let it be this. Stop trying to brute force memorize hundreds of individual reactions. Instead, shift your focus to recognizing the patterns, the simple swaps, the connections, the bridges that link everything together. So here's your new mission. As you go back to revise, use this framework. Don't just learn a reaction in a vacuum. Ask yourself, okay, how does this connect to another chapter? Once you start to see the whole map instead of just one road at a time, organic chemistry stops being a chore to memorize and it becomes a puzzle that you can actually solve. Thanks for watching.